All right, welcome back. More about energy conservation. We're going to tackle an example to see what we can really do with this idea that energy is neither created nor destroyed, it just changes between different types. The types that we're concerned about are all mechanical energies, so we're going to really look at uh, kind of three things. Potential energies, we have two of those, gravitational potential energy and spring potential energy. And then of course, kinetic energy, which we have two of, translational and rotational. So we're only going to consider kind of four things. But our total energy only changes through work done by non-conservative forces. Remember our master equation. Change in energy equals work from non-conservative forces. So let's look at this example. Crate starts at rest at the top of a frictionless hill, height of 10 meters. It slides down the hill, and at the bottom it encounters a rough surface. It slides along that surface. Coefficient of kinetic friction 0.25. How far along the rough surface does the block slide before stopping? Now, in principle, we could solve this with a combination of Newton's laws and forces along with kinematics. We could use Newton's laws and figure, okay, what's the acceleration down the ramp? We could say it starts at rest. What's the final velocity at the bottom of the ramp? And then, oh, now I have a new acceleration, which I could calculate from Newton's laws along the flat part where there's friction, and I could figure, oh, now how far does it go before it gets a total final velocity? That seems like a lot of effort. We're going to do this much quicker with our energy conservation model. So remember, again, master equation, change in energy equals work from non-conservative forces, or final minus initial energy equals work from non-conservative forces. And I have 3 points here, A, B, and C. We really need to only consider energy at point A and energy at point C. Energy at point A is the initial energy, and energy at point C is the final energy. So let's look at those really quickly. And this is general technique for all of these energy conservation problems. A beginning state and an ending state. The stuff that happens in between, the details of that doesn't matter so much, only in calculating work from non-conservative forces. But we really want that beginning state and ending state. And so let's look at that beginning state first, initial energy. And we can run through the list, those 4 things I mentioned. Kinetic energy, translational kinetic energy, rotational kinetic energy, then gravitational potential energy, and spring potential energy. What types of energy does the object of interest, the thing of interest, possess in this system? The thing of interest is that crate that's sliding the block, right? So, well, it's not moving. It says it starts at rest, so it has no kinetic energy of either kind. There are no springs anywhere in this problem, so we don't have to worry about spring potential energy, but we do have gravitational potential energy. Remember, if we look up the formula for that, it's m times g times h. And in this case, 0 high is right there. 0 high, which is also the same place we'd have 0 gravitational potential energy. So it really has mgh amount of energy right there, right? Final energy is, well, what's the energy at point C? Well, it's no longer high up, so there's 0 gravitational potential energy. Still no springs, no spring potential energy. It's not rotating, absolutely 0 rotational kinetic energy, and it's not moving anymore at all, so it has 0 total energy. Final energy state, 0. It came to a stop. The last thing that we need to figure out is the work done by non-conservative forces. Now, conveniently, the work done by non-conservative forces is only between point B and point C here. That's the only place where we have friction. So I'm going to draw a quick sketch of our box there and look at, I'm going to have to look at some forces because, as we know, work involves forces, right? Normal force, mg, gravity down, right? And then some kinetic friction backwards. That's really it, right? And we can quickly, because we're now all experts with Newton's laws, go, oh, friction, that's going to be the normal force times the coefficient of friction, which will of course be the normal force will of course be equal to the gravity here on this horizontal part. So I can say kinetic friction equals mu k mg, and I can just do that pretty quickly with maybe that quick sketch, and then skip a few steps of what we used to do more explicitly with Newton's laws and say, I can see that's the case. Work from non-conservative forces. This is the work done by friction, right? So I do integral f sub k dot ds. ds is little bits of stuff this way. Oh, look, they point in opposite directions. The dot product of exactly opposite direction forces is minus the regular product of those two things, right? So I just go minus integral mu k mg ds. I plug everything in. And then, I go from 0 to d, distance d, right? Mu k times m times g, that's all a constant, it comes out. I end up with the work done by non-conservative forces as minus mu k m g d. That's the friction force times the distance over which the friction force acted with a negative sign in front of it. That negative sign means friction is really sort of removing some energy. And really what it's doing is it's converting it into thermal energy, but it's energy that we're not going to recover back into our mechanical energy considerations. So now look at this. I have 1, 2, 3 things that I can plug into my master equation up top. Let's go to the next page and we'll do that. Final energy was 0 minus initial energy, mgh, equals the work done by non-conservative forces minus mu k mg times d. And we wanted to know distance d. How far does it go? Oh, look, conveniently 0 minus. Those minus signs will cancel out, right? It's a good thing that mass is on both sides, and I can cancel out mass because I didn't tell you what it was, right? Could have made an analysis of Newton's laws a little bit tricky, but it works out here. A little bit of math later. Oh, let's cancel out g as well. That'll go out. But a little bit of math later, I can get d equals h divided by mu k. That's 10 divided by 0.25, or 1/4. That's 40 meters. Way easier. That took a lot less time than it would have if we had done that problem using Newton's laws and kinematics in some combination. This energy conservation technique where we look at final energy of the system minus initial energy of the system equals the work done by non-conservative forces. That is the go-to problem-solving technique for physicists. The very first thing we try with almost any system is to try and do energy conservation because we have not found any exception. Energy is conserved. I can't destroy it. I can't make more. All I can do is change it from type to type. And that's super duper important, and it works everywhere in the universe. Sometimes writing down the energy terms gets pretty complicated mathematically, but for our purposes, this with mechanical energy is what we're going to stick to in this class. It doesn't get too crazy, and we really always want to consider those 4 things: rotational kinetic energy, translational kinetic energy, spring potential energy, gravitational potential energy. That's it. Go through that list every time to write down what's the energy in the beginning state, what's the energy in the final state, right? And you do final energy minus initial energy equals work from non-conservative forces. We know how to calculate work from non-conservative forces. Mostly for us, that's going to be friction. There might be a problem or two with air resistance involved, but we also know how to do that. Let's look at one more example. A rough ramp with a coefficient of kinetic friction given a length, given 3 meters. That's the distance from the top along that diagonal, along the ramp itself. Set at an angle 30 degrees from the horizontal. Then there's a frictionless track with a loop of radius r. If you do some quick YouTube searching, you can find people trying to do homemade water slides off of their roofs, and you can see that probably none of them took a physics class because there are some pretty traumatic failures. I'll see if I can find the cool video and maybe I'll post it on Canvas. If anybody else finds it, let me know. But what we want to do is find out how big a loop can I make and still make it all the way around. I want to make it all the way around the loop. I'm still going to use energy conservation. So I still need to figure out what's the energy before and after and all that. But I'm going to look at some particular spots. I want to look at spot A and spot B. Spot A is up there at the top. That's the beginning state. Spot B is really the critical point for make it all the way around the loop. At spot B, at the very top of the loop, here's what's critical about spot B. I need to have some velocity, I'm going to call it velocity at point B, going that way. If I don't, then I've come to a stop and the block just falls straight down and it's all over and I didn't make it around. If you find some homemade water slide loop-to-loop videos, you'll see that a lot of people don't make it all the way around and they end up falling off of the loop. So in order to relate this to stuff that we want to know, we're actually going to have to look at forces. But before we do that, let's use our energy conservation model and see what exactly we need to figure out. Delta E equals work from non-conservative forces, right? Well, E at point B minus E at point A, final minus equals work from non-conservative forces. Energy at point B, that's going to be a little bit complicated. Let's look at it. Is it above zero height? Well, I'm going to call the lowest down point 0 high. That's where I measure all my heights from. So I'll say this is height equals 0, right? That means that at point B, I'm the diameter, or twice the radius that I'm going to be looking for high. So that's that radius I'm looking for, capital R. So I have gravitational potential energy, mg times 2r high. But I'm also moving, right? So I have kinetic energy, translational kinetic energy. No springs, not rotating around its own axis. That's what's important for the rotational kinetic energy. So I can just add in that kinetic energy term, 1/2 mv at point B squared. I don't know what v at point B is. This is going to be a tricky thing we're going to have to figure out, but let's not go there quite yet. We want to look at the energy at point A. Well, it's not moving. It said it starts at rest, so no kinetic energy of any kind. That's 2 of our 4. Then there are no springs, so no spring potential energy. And, gravitational potential energy. How high up is it? Oh, what's this height right here? Height at point A. Well, a little bit of trigonometry, we can figure out that this is, let's see, that's got to be d sine theta, where theta is equal to 30 degrees. D is that 3 meters, the length of the ramp. So I can say this is mg d sine theta. And that's the only kind of energy that exists there to begin with, right? Then work from non-conservative forces, well, it's going to be friction. Here it's a little bit trickier, right? Because now friction, than our last example, it's trickier. Friction is opposite the direction this block is going to slide down the ramp. The normal force is not exactly equal to that. And the gravitational force, now I got to do some weird stuff with a theta. Go back and look at some of the blocks sliding on ramps that we did in the forces section, and you'll pretty quickly see that normal is equal to mg cosine of theta. So the friction would be mu k times the normal force, right? And this mu s up here, I think that should be a k. The coefficient of kinetic friction. And then the work, once I figure out that force of friction, the work is that times distance d. I'm going to get minus mu k mg g d cosine theta. Take a second, convince yourself that that's the case. But I have those three things, but I still have an unknown in addition to my unknown radius r, velocity at point B. This is where I really need to turn back to forces because, oh, well, there is some velocity that's tangential velocity, tangential around that circular loop, right? So that's kind of like a centripetal thing. And that force that's in there, mg, that's a centripetal force. It's a force on the block towards the center of a circular motion. And I want to take the limit where that's the only thing where right at the very top of that loop, the block just starts to almost come out of contact. The normal force goes just barely to zero. So the only force acting is mg, as shown in the diagram up there. But it's a centripetal force. That means that it must be equal to the mass times velocity squared over radius. Oh, look at this. Masses will cancel out, and in fact, I can get velocity at point B squared as g times r. That's going to be super handy. I can plug it in right there as g times r for that whole vb squared, right? Now I can use this and I can chug everything into my master equation again and see how far I'm going to get. So energy at point B, we had 2mgr, right? And then I had plus 1/2 mvb squared, but vb squared is just gr. Oh, this is working out well. That's final energy minus initial energy. That's minus mg d sine of theta, right? Mg times how high it started. And that equals the work done by friction along the friction-y ramp, the rough ramp, where mu k, let me fix that here too, 0.4, I have minus mu k mg d cosine of theta. And it's really mg cosine theta times mu k times d. I've just rearranged it to make it match our other stuff a little bit easier. And what I really want to find here is r. So let's, at this point, I would say I'm really done with physics. I have a single equation with a single unknown r. All I've got to do is finish the mathematics. But let's do that really quick, just for the sake of things. I've got 2 mgr plus 1/2 mgr. That's 5/2 mgr. If I add those all together, and I'll keep that on one side, and I'll move everything else to the other side, I'll get mgd, and then I'm going to actually factor out some stuff. I'm going to have sine of theta, which I had to add to the other side, minus mu k cosine of theta, right? Oh, look, m and g cancel out. Doesn't even matter how much mass I have or what planet I'm on. Awesome. I can just solve this for r, multiply by 2/5 of d times sine theta minus mu k cosine theta. And I'll leave it to you to crunch numbers in there with d equals 3 meters and theta equals 30 degrees and mu k equal to 0.4. That is a good example of energy conservation. Take a look at the homework number 8. Try those problems post discussion section, discussion post questions on there. You might hear a dog whining in the background. She thinks it's dinner time. You hear Sophie? Can you hear that, Sophie? Yeah, now I'm paying attention to her. So I'm gonna go feed a dog. You guys work on your homework. I'll see you in the next video.